All right. So we have chromium iodate here, and we have been asked to figure out the molar solubility of this chromium iodate. We have a value for the KSP, so we should be able to set up a KSP expression and solve for the concentration of the ions and then relate that back stoichiometrically to the compound itself. But first, you got to be able to draw the compound. Iodate's not a super common ion, but it is a -1 ion, which means that if I have a 3+ charge here and a -1 charge here, I'm going to need to end up with 3 iodate anions. When that dissociates, it's going to release a chromium, and then it's going to release all 3 of those iodates. These guys over here are both aqueous. And this guy over here is a solid. Now, if I set up an ice table, right, initially, there's none of those ions. There's a bunch of the solid, but we don't care because it's a solid, so we're still just going to leave a dash there. My change from the solid to the ions is going to be a 1 molar change for this chromate, because there's only one of them there. But it's going to be a 3 molar change for this iodate, because there's 3 of those there. And that's very important that we remember that. Then we just bring those down for the equilibrium column. And as a reminder, if you put X here, it doesn't matter. The X's will work as well. We just use S for whatever reason. Now, quickly set up the general KSP expression, assuming that we didn't know what the concentrations are. And by that, I mean just put the ions in here. Okay. Remember that you have to take the stoichiometry into account in the KSP expression, and you're going to have to cube that iodate anion. Now, it turns out we actually know values, right? So we can change from the ions to the variables that are now representing them. I have the 3s from the ice table, and then I have the cube function, and I'm going to have to put those guys together. And by together, I mean when I solve, I distribute that 3 out to both of those. And then I end up cubing the 3. And so that's 27. And I end up cubing the s. So it ends up being 27s cubed. Or to simplify it even further, 27s to the 4th power. Now I know the value for KSP, and I'm going to scoot over so I have enough room. There's my value for KSP given to me in the problem. And I've already simplified the other side of my expression, so I can quickly do that. Divide both sides by 27, and then take the 4th root of that. In your calculator, you're going to type in, or what I would type in my calculator, would be 5.0 times 10 to the -6 divided by 27 caret 1/4. So this caret raises it to the 1/4 power, which is the same as the cubed root, which is what you need to do to get rid of that, not cubed root, but the 4th root. And so when we do that, we get a value of X of 0.0207 molar. And it turns out, here, let me change that to S so I don't change anything. It turns out that S is actually the concentration of the chromate 3+ that dissolved in solution. But since this is in a 1-to-1 ratio with the salt itself, then we end up saying that the molar solubility is equal to this as well. That's the molar solubility, 0.0207. As a note, maybe the question would have said, what's the concentrations of ions in solution? This would be the answer for the concentration of the chromate ion. But if you went back here, you'd have to remember that it's actually 3s for the iodate. And so it would be 3 times the 0.0207 or 0.0622 molar for that.